From the 3 Degrees discussion studio, I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
Yeah, so we use height as our inspection feature. And the height spectrum is really interesting. It can detect defects in any layer of powder that's spread before any melting or solidification even happens. We're able to see streaks, hops, spatter, short feeds, build plate skew, anything that is deposited during the build, and get a quantification and a height cloud of all of those points.
That was Niall. Niall is the founder of Phase3D, a company providing solutions for part monitoring and process control for additive manufacturing. Niall completed his PhD in structural engineering from the University of California, San Diego, and joins us today to talk about his entrepreneurship journey. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast, where you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Also, if you or your team are looking for materials, qualification, or general additive manufacturing support, reach out to our team through our website or via email at info@3degreescompany.com. All right, Niall, thanks so much for joining the show today. Super excited to have a local guest on the podcast today. So we start like we do with everybody else, kind of from the very beginning. So where were you born, where you're from, and what were some of those early memories on kind of getting into engineering, getting into science?
Yeah, thanks a lot for having me. Really appreciate it. I love the show and happy to be featured on it. Yeah, so I'm from Seattle. I grew up in Seattle, Washington, did some school out in New York State, and really got into advanced manufacturing through my PhD at University of California, San Diego. It's a great place to learn about additive manufacturing, the challenges of the industry. And throughout my undergrad and graduate school, I worked closely with the Los Alamos National Lab, specifically structural engineering. We were doing structural health monitoring, which is the science about inspecting structures, which could be aerospace structures, civil structures, the manufacturing process, pretty much everything that is built, deteriorates over time and needs maintenance, repair, replacement. And with advanced signal processing and these advanced electronic systems, we're able to really target and interrogate these structures in a way that can help us figure out when these things need repair or what state they're in. And so I learned about additive manufacturing, the potential for the metal additive manufacturing industry, production parts, and we learned a lot about during my PhD the issues and the challenges towards getting to that end use production, the first time right printing, and qualification and certification of these amazing parts that can be printed but not necessarily approved by all of the certifications, qualifications of the chain.
Do you have an early memory of like what was an interesting thing that got your mind, like your curiosity going about? I mean, don't want to say like inspection or something like that, but like, were you a tinkerer? Did you like taking stuff apart? Did you have like a class that you liked, like growing
Yeah,
up?
so actually in high school, I was obsessed with the sculpture department. And so I kept going back to sculpture, and I started an independent study in this strange little department in this room in my high school called the Department of Making Things. And it's basically we'd go up into the library building and then go up to the second floor and then go through this one door, then go down some stairs and then go up a couple of stairs. And there's this man in this room surrounded by laser cutter, a cupcake maker bot, a laser engraver, this room that nobody really knew about. And I would use the laser cutter to make different kinds of like a disco ball and stencils, multi-layer things. And I remember using SketchUp to make this FDM like octopus type thing where these parts were shoving into each other and the tolerancing was all messed up, and learning about you know, how much overlap does there need to be? How much space should I leave between all of these different parts? So really from then on, just interested in ways I can go from a computer design to a physical part without actually having to use an X-Acto knife for an hour and a half to cut something or build something or shave off something. It's really, exciting time to be able to make something on the computer and then see it in your hand the next day.
So maybe going back to kind of your undergrad days,
Yeah.
did you always think that you were going to do a PhD? Was that a roadmap that you had kind of
No,
built out for yourself?
I didn't really realize that that was a thing until I did my first internship slash co-op at Los Alamos National Lab. So when I was an undergrad, when I first started school, I really wanted to do something creative, but also something involving physics and engineering. And I thought being a mechanical engineer would be a way to exercise analytics, mathematics, physics, but also something creative, design, making things. But throughout my undergrad, I felt like the engineering was not as creative as I would have liked. And so in my final year, I was kind of gearing up to do a product design or some kind of industrial design master's degree. But then I did my final co-op at Los Alamos National Lab. And the National Lab system was so exciting because everyone's doing all of these things for the first time and creative problem solving, publications, notoriety for doing things new or better or differently, thinking creatively how to solve problems with an immense amount of resources was so much more interesting than solving the same problem for a customer with the same templates from 10 years ago. And, doing a PhD, seeing everyone around me with their PhDs, it really felt like the most exciting path that I could think of is really, scientific innovation like that. And it kind of brought together the creativity that I was missing in the engineering undergraduate world and people just sticking their flags in something and publishing it. And it was really exciting. So,
For for those uninitiated with the national lab system, do you want to just give kind of like an overview of what it is? I mean, by this
yeah,
point, some people have seen Oppenheimer, so they have a
yeah,
little
yeah,
bit of an
perfect.
idea, but
Yeah, yeah. Oh, yeah. So, yeah, I think Argonne National Lab was actually the first Department of Energy US national lab that was established. And the national labs, there's more than 10 of them, I think less than 20 of them in the United States. They're established in the 40s. I think Argonne was maybe 1939. But essentially, they are powerhouses of federal research sprinkled throughout the United States. A lot of nuclear research, nuclear energy, nuclear weapons, environmental science. Really, it's a lab that is able to conquer and answer questions that just take too long to answer for more commercially funded labs. For example, Argonne has creep experiments that have been going on for 60 years, material in an oven that it's from 60 years ago, and it's for testing for materials to go into nuclear reactors. They can extrapolate the creep results times two or maybe 50%. I mean, don't quote me, but they have to test these materials for decades and decades. And so before they are approved for nuclear safety. And so I think the US government realized that there is the science that doesn't really fit into a commercial or even a university funding cycle that really will help national security for the United States. So Los Alamos, pretty notorious one. Um, we work with Argonne National Lab in Chicago, Oak Ridge National Lab and Manufacturing Demonstration Facility. It's like Costco for 3D printers. There's $100 million worth of 3D printers in there, some really experimental ones, some great stuff going on there. So it's really like just you know, a great way to achieve, get some of the greatest scientists in the US and get that funding and the expertise to solve some questions that are pretty large questions.
so do you remember the first time that you saw 3D printing? So was it that high school class that you had with the cupcake system, or was it
Yeah.
something else?
Well, it's probably the first time I brushed my teeth, I would say, with extrusion-based 3D printing. So,
Yeah,
um, but yeah, I was basically in that department of making things. But I think there's a lot of 3D printing people don't really think about, like toothpaste, any
for
kinds of
sure. Yep.
extrusion, um, you know, making frosting. That's 3D printing. So.
Yep. Yep. Awesome. And so you're doing the PhD. Did you have an idea of what you wanted to do kind of next or after that was completed?
Yeah, so I was fortunate enough that my PhD topic was something that was able to choose that was more relevant to the current state of the industry than the majority of PhDs. So lots of times these research thesis questions will be focused on the a pinprick of something so advanced that it's not commercializable. It only affects 10 people in the entire world. It's commercializable, but maybe in 100 years from now. Um, but after I did my whole literature review on, all of the methods of in situ inspection and really learned about the challenges and the the applications that would be able to be accessed if we could print with high quality inspection part guarantee. I realized that then my PhD thesis was so applicable to the industry, and there was a way and a method to commercialize. So after I filed um, my first paper to get all of the required numbers because
Yeah.
Los Alamos was still funding the research at this point. I talked to my advisor and we were able to you know think about solving the system in a usable way or solving the challenges involving part quality in a way that's immediately useful for the industry. And that kind of led me down the entrepreneurship pathway and towards exiting academia and building a company.
Did you have any mentors or people that you saw doing that path? Because I mean, I think sometimes we kind of take it for granted of like it's not easy to start a company. There's a lot of risk, right? Especially coming from a, a PhD is a little bit different, but like certainly a national lab where it's like, hey, regular paycheck, like you're funded
Right.
by the federal government, like generally pretty stable, things
Yeah,
like that.
my advisor for my PhD, um, he was really inspiring in so many ways, and just basically, your PhD advisor has the potential to make you miserable forever. Um, but that was the opposite of what he did for me. Um, but he actually told me it was too risky for him to do a startup at this stage. So um, he wasn't a mentor to me in particular for entrepreneurship and building this company. Um, but one of my earliest mentors was my first advisor or boss manager at Los Alamos National Lab. His name's Eric Flynn. He's won two R&D 100 awards in structural health monitoring for his invention called acoustic wave number spectroscopy, which is the system that uses steady state ultrasound excitation and a laser Doppler vibrometer to measure thicknesses of plates. So you can imagine a swimming pool or a puddle, and if you throw a rock into the puddle, you can see the waves, and the wider the wavelength is on the surface, the deeper the puddle is. But with a really shallow puddle, the waves are bouncing, and the waves on the surface are close together with a
Sure.
short wavelength. So basically, we would put this ad hoc ultrasound um, vibration device, which was actually sold as a jewelry vibration system to send ultrasound through a medium to clean jewelry. We'd clamp it onto a plate with corrosion or a composite plate with a delamination. Um, we'd send steady state excitation So the thing's wiggling around like this, vibrating. Then the laser Doppler vibrometer measures each point, and we calculate the wave number, which is just the inverse of the wavelength. And areas with high wave number, meaning short wavelength, um, we can calculate the thickness of the plate. And so it was really exciting working on such an emerging technology in sensing. And he put me on a project to support this feasibility test with Shell, and we were doing. I would travel down to Santa Fe, and we did some measurements on oil tanks, and it was just really interesting and exciting developing the technology that no one has ever done before, no one has ever made work before, and also getting that exposure to real customers who give a shit about what you're doing. Because sometimes at the national labs, it's just like, oh, no one cares about this paper. You find yourself just toiling over some small detail, but seeing the bigger picture was really amazing. And it was funny. We were competing with, we set up the system, we set up the tripod, we get the map, we have the graphics user interface, and we're like, here's the defect, here's the average thickness of the plate, and it's a big win. And then we're competing with the status quo, and the technician comes up with a single point ultrasound probe and just comes in high confidence and measures 1 point on the plate and is like, see, I can just measure that, this is the thickness, but it's like actually, we have millions of points of measurement, and we can do this in a dangerous environment, an extreme environment. But it was kind of, foreshadowing to you're always competing with the status quo and the confidence of whatever comes before. And in this case, it's just one guy with one measurement point taking three samples of a plate. So it's kind of interesting, like the new technology and the amount of convincing or the amount of business development required to make an impact. It's not just based on the technology, it's based on the story.
Yep. And so maybe talk about kind of the some of the early days of going into to start a plan. What was that like? What was your kind of mindset? Did you know was it what you expected? Was it completely different? Like when did you kind of make that kind of mental transition into
Yeah, so
that space?
really, I had to deprogram myself at the end of my PhD from caring about things that were so technical. So, when you're doing academia and developing a technology and building a prototype, it's easy to think that the value proposition is resolution or other kinds of technical parameters that you find that you publish on, oh, our standard deviation is this. So if someone were to ask me, what's the value proposition of your technology? It would be, oh, 5 micron resolution and 10 micron pixel patch spacing. And then you walk away because that's what was so impactful in the research community. But, it doesn't really correspond to value proposition at a company or in a business. And so the way that I was able to really like deprogram myself or reprogram myself was through the National I-Core program, which is a National Sound Science Foundation program, that there's regional nodes hosted at many different universities and national nodes hosted at other universities. And it's basically a way for anyone involved in academia, grad students, undergrads, associates, to basically validate their ideas of inventions in a lean startup framework with a really rigorous community of experts. So at UCSD, there's an NSF Core program that I joined, and it was really a way to learn about lean startup, learn about the business model canvas, learn about customer archetypes, product market fit, and in a way that kind of lets you look at your invention from a different perspective. And the most valuable part of that program and the follow-on program, the National I-Core program, are these customer interviews. So I was basically able to learn a method to validate the market, not focused on our invention, but on the needs and pains of our customer profile. So through these customer interviews, we would ask um, over 100 customers, which are just basically anyone in the additive manufacturing community, questions about the pains, how things work, without saying product forward questions, without asking, would you buy this? Do you think this is useful? Here's what we're developing. Isn't it great? But it's more about, what is the worst part of your day? What do you feel afraid of when you're using metal 3D printing? What's the worst thing that can possibly happen with a build? What happens after that? Who's responsible for that? And with those questions, it can help you validate if your idea is useful, valuable, or if it's just something that's kind of technology centered, but not necessarily application centered. And I knew I had really screwed with my programming um, when after I finished the national iCore program for 100 customer interviews focusing only on product market fit, value proposition. The first SBIR phase one that I put in the project pitch for from the NSF, we got rejected from the pitch, the 1 page pitch or the 2 page pitch, and the comments were just, there's no information about the technology at all. And I reread the pitch and it's just only the value, the customer, the problem statement, product market fit, why it matters, broader impacts, but I had completely left out any information about what the thing actually is or any kind of scientific technical merit that I've been working on after this rigorous program. So I knew at that point, you know, my brain has been brainwashed into the business and the value of the technology and not specifically PhD technology.
I think
Is
that's where
what
we first
that's
met,
what we
right?
first. Yeah,
So, and
yeah.
and then when did you land in Chicago? So you were at UC SD. When did you decide 80 and sunny every day was not what you really wanted?
Yeah, I did. Yeah, I interviewed you for the NSF program. I
Yeah,
remember.
I don't know if I was probably not useful, but
Everyone was useful. Yeah, I have that recorded. Everyone I talked to is recorded in an Excel spreadsheet. So, and all the notes. So that'll be fun to go back and look at. Yeah. So as I was wrapping up my PhD with about 1 year left, I talked to one of my friends who had recently graduated, and he told me about the lab embedded entrepreneurship programs. And these are programs sponsored by the Department of Energy, specifically the Advanced Manufacturing Office, which I think is rebranded with another acronym, maybe AMTO or AMMTO, something. But when I was applying, it was the Advanced Manufacturing Office, and essentially at these national labs, Oak Ridge, Argonne, Berkeley, Lawrence Berkeley, and I think some others have added like NREL. But essentially, it's a program that will fund about 4 to 5 entrepreneurs a year who are working on deep tech and climate tech innovations and building companies that will address climate change and sustainable manufacturing or sustainable activities that support the US on building a more sustainable future. And so I applied to Chain Reaction Innovations, which is the Argonne Leap node. Um, and when I won a spot, um, and it's a fellowship program that provided a stipend, research and development funds, facilities, entrepreneurship programming, travel stipend, really the whole package. But most importantly, close partnership and a credo with Argonne National Lab in Chicagoland. So that's what really got me out here is winning this fellowship and having the space to start planning and really making my dreams of starting Phase3D a reality with the help of the US National Lab System, the Department of Energy, and all of this facility space that was available to me through the Chain Reaction Innovations program.
Cool. And do you want to talk a little bit about what you guys do? What's the technology, and kind of describe it
Yeah.
for the audience a bit?
Yeah. So, when I imagine advanced manufacturing and metal 3D printing and all of this amazing technology, I think of a facility with the lights out, conveyor belts, automatically producing these advanced parts with high part quality guarantee, um, no supervision, on demand, and addressing supply chain issues like the technology really has a potential for. But in reality, metal 3D printing at a production level quality is at its relative immaturity compared to other kinds of manufacturing that have been tried and true for 100 plus years. And so, as soon as we can overcome the challenge of part quality, part variance, and have the certification, inspection, and qualification to prove that part quality, we can be back into the production level and the exponential growth that we're all expecting. And we know it can be done in the additive industry. And so that's what my company does. We're focused on unlocking that next phase of additive manufacturing through real-time inspection and part certification. So we can transition from prototypes to those end use parts with high confidence, high throughput, and those amazing designs you see, which are only achievable through these advanced manufacturing techniques in additive manufacturing. And so we've developed this product called Fringe, which is an in situ inspection system, which inspects every layer of powder bed fusion, binder jetting. We're working on our cold spray variant. Essentially, we can inspect every layer before and after the binding, the melting, or the spraying process with real units that can be used for immediate defect detection, part certification, and just holding your printer accountable for what it's actually doing, what features are being actually printed in the part in a reliable and completely data transparent way, not relying on a neural network. And really, our focus is developing these inspection systems that can be built into certification qualification for these advanced parts.
Awesome. And so when you say kind of validating layer on layer, what are you looking for specifically? Is it an image defect? Is it a temperature or some other sensor probe that or signal that you're looking for? Can you give us some insight on kind of what for
Yeah.
maybe not in
So
detail, but like what does it mean what to see a layer good versus bad?
yeah, so we use height as our inspection feature. And the height spectrum is really interesting. It can detect defects in any layer of powder that's spread before any melting or solidification even happens. We're able to see streaks, hops, spatter, short feeds, build plate skew, anything that is deposited during the build, and get a quantification and a height cloud of all of those points in the chamber or the measurement area. And then we use height again after the binding or the melted layer is exposed to look for any changes in areas that shouldn't have changed dimensionally, or where the spatter agglomerations land. Did the layer get fused correctly? Did the layer get bound correctly? Um, and we found that using the height spectrum, it's a quantifiable feature. It's not subject to different lighting conditions. It's not subject to different emissivity. It's a material independent feature. And we're able to quantify these build anomalies and part defects with real units, which we found is really important for NASA in situ monitoring work, and other customers who need something that's highly quantifiable in terms of part acceptance.
So, I mean, we're in adjacent spaces, certainly in terms of collecting data around materials and traceability. One of the harder questions I get for this, and I always think about, is you take older technology, the castings and forgings and things like that, technologies that weren't developed with alongside digital data tracking, data modeling, things like that. Um, One argument here is like, hey, just because we have all of this data available, how do we make it distilled in such a way that an operator can make a decision about it, right? It's one thing to capture it, but what's kind of a um, for you guys, where's the hey, red light, green light? Like, do you guys are kind of getting to that point where you say, okay, we know like if you see enough of these height deviations, you got a problem? Or is that something that as you develop it with your partners and your customers, you kind of learn along the way to say, okay, hey, we've got more of a window than we thought. Like maybe we can decrease the resolution. Like where are you guys thinking in terms of that development?
Yeah, so it's a really big issue in the in situ monitoring, data collection process recording industry is, you know, okay, you have this in situ data, so what? What do you do about it? Do you need a supercomputer, a PhD, a material scientist, or an intern to look through every single layer and figure out what's going on? So we've really built our system with the constraint in mind that there needs to be an action, whether it's a binary action, whether it's set by the technician in allowable thresholds, whether it's calculated automatically by a history of the part, either porosity or fatigue life. And so through our partnership with Argonne National Lab, we're able to do this validation work. Essentially, we recreated these anomalies, which we measure in titanium, and we were able to take at the advanced photon source, we're able to take these high-speed X-ray videos of the sintering process and see in real time, you know, this lack of powder or this powder streak. Um, Really, we watched it and we quantified the amount of powder that causes a keyhole pore. And so we can find these pores and find the melt pool penetration depth with these advanced X-ray machines or serial sectioning or CT scan. And we're detecting the predecessor for these part defects, and so finding the correlation between the print defects or the print anomalies and the part performance. And that is really where we see the value and where we see that go and no go gauge. It's not necessarily based on something subjective like a shadow, but it's more based on, is this anomaly going to create an 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 increased layer of porosity in the part, or is this anomaly going to create higher variance in fatigue life for the build, all of the parts on the build? And that constraint is really important to our system and the design of our system and the development of our system, because data can get pretty large pretty quickly. And if there's no feedback for the technician, there's no user profile or user setting for the technician or the build manager or the build engineer, it's really hard for them to, gain value from the system.
Sure. And so switching away from the technical a little bit, or this may overlap, but as a kind of founder of a company, what's been one of the most unexpected things that you found in running your own thing?
I think being a solo founder and building a team has been the most difficult challenge. Um, but I'm really happy to report that, we have a strong foundational core team developed that is really able to fulfill all of the different aspects of the company and work synergistically with each other, communicate with each other, But that the team building aspect as a solo founder in particular has been a massive challenge in going from uh, PhD researcher managing projects and only having to communicate with myself to building a team and a community and a community space has definitely been the biggest challenge, I think. But it just gets so much easier as new people get added to the team and we start to grow. It just brings me a lot of energy and brings so much value having dissenting opinions, multiple skill sets, different ideas coming to the forefront that, I would have never thought of, the person next to me would have never thought of, but the new person, that's really what has been the most challenging, but also the most exhilarating part of building the company, I would say. And also just breaking down, there's so many things that I had to become just good enough to pass by. And I kind of forgot that, people, it's just been for the last couple of years, it's been having to do whatever's needed and not really think about, oh, I want to do the mechanical design. That's what my job is. It's more just like, oh, I need to review this patent now. It's like I have to become just good enough to read a patent and figuring out what the claims and the abstract and the background means and is used for. And then the next time it's, oh, what's the trademark in Illinois? I have to become just good enough to read an electric diagram and recreate or do testing with an oscilloscope, just good enough in electrical engineering. And it's been so much of just doing everything that that's been difficult. And I've just forgotten like what it means to have a one job description, I guess. So there's another one.
Cool. And just last couple of questions. So, do you have a favorite book or a book that you'd recommend to kind of people that gave you some inspiration or some ideas in terms of how to run your business or kind of or was impactful in any way in your life?
Um, Really, the Lean Startup um, book was pretty impactful, and the lessons that were distilled in some of the chapters that I read during the NSI core program is really interesting. Defining a startup as more about activities done at the company versus the size or how old it is. So it's really interesting learning about the startup. The purpose of the startup is to, as inexpensively as possible, search for a repeatable business model that can scale. And once you find that business model that can scale, you can build something that's more rigid and enter your scale up mode. But that could take 10 years, 20 years. You could be, a million ARR, 10 million ARR startup if you're still searching for that repeatable business model. Um, but it's about, the stages of a company and the difference between a startup and just a tiny non-startup company. Like you can have a company that with 5 people that's executing, that has already scaled up, that's found the business model that works, that's repeatable. And you could be 6 months in and no longer a startup, or you could be, VC funded with 100 million and 1,000 employees still searching for that business model. And I think you'd still be considered a startup. So it was really interesting to know exactly what a startup is, what a scale up is, and what a company is, and know that startup's not just a small, tiny company or baby company. It's another interesting mindset.
So last question. What are you excited about for kind of the next six months? Are we going to see you at any of the trade shows, or where can people come find you, see what you do?
Yeah, so Noah Mastow, our business development manager, will be at Formnext Forum. He'll be wearing this jacket, pretty easy to find. We're exhibiting at the startup area in Formnext in November in Frankfurt. So really excited Love that conference. We have some exciting new technology developments and new partnerships to announce for that, with their secret for now. So really excited for the next 5 months and kicking off our cold spray project with Ellsworth Air Force Base and UDRI. We're just finishing our successful phase 2 with Tinker Air Force Base. We're on the heel end of our NASA Marshall Space Flight Center project. Soon to announce some more commercial partnerships, in addition to the DMG Mori partnership, a research collaboration, Materialize partnership. So really, it's been an exciting road getting integrated into the AM ecosystem and being able to provide a tool that can be used by the users of the technology, the end users of the parts coming from the technology in terms of certification, the machine tool builders who are interested in getting quantitative data from the process, and really, entering the market and building our presence in the ecosystem has been really exciting.
Fantastic. Well, thank you so much for joining the show today. Excited to see you around the industry, around Chicago. So awesome. Good work.
Thanks so much.
Stuff.